Hi there. My name is Ashley Sear, and I'm a Business Development Manager within the Imagery and Remote Sensing team at Esri Inc. Today I'm going to talk about reality mapping as a key enabler for digital twins and 3D GIS, and more specifically about creating reality mapping products from drone, aerial, and satellite imagery. In recent history, the world has been marked by a series of devastating storms, each leaving a trail of destruction in their wake. As we delve into the impact of these events, it's crucial to understand the magnitude of their effects on the communities worldwide. In the United States, Hurricane Helene made landfall in Florida as a Category 4 hurricane, bringing catastrophic flooding to the southern Appalachians. The sheer force of Helene's winds and the volume of rain it unleashed resulted in significant damage to infrastructure and homes, displacing thousands of residents. Following closely was Hurricane Milton, which compounded the challenges faced by the affected regions. Milton's torrential rains and strong winds led to the widespread power outages and further flooding, hampering recovery efforts and stretching emergency services to their limits. As storms continue to ravage communities worldwide, it brings us to ask, how can we leverage the best and most innovative technology on the planet to be more prepared? During this workshop, I'm going to take you through a journey of how digital twins and 3D GIS are helping us to make better decisions for our future. By leveraging digital twins and 3D GIS and reality mapping, we can monitor storms in real time, predict their paths, assess potential impacts with greater accuracy. These technologies enable us to visualize and analyze complex data, provide critical insights that help us prepare for and respond to these powerful weather events. Instead of waiting for these incredibly powerful storms to pass, not knowing where or how long recovery efforts might take, let's explore how we might predict and prepare for these storm events. To ensure our cities are equipped for what is coming, we can allocate resources appropriately and ideally mitigate damage before it even happens by modeling the impact to infrastructure. In this example, a 25-foot flood scenario is calculated to assess the impact to water crossings, railroads, roads, and buildings. Land managers and scientists use 3D GIS to create environmental digital twins that integrate knowledge about ecosystem health and biodiversity. Digital twins capture how ecosystems are now and how they will change. By sharing data and knowledge, environmental digital twins foster collaboration across scientific domains. Another form of collaboration across scientific domains is in the historical realm. The Giza pyramids exemplify good management, showcasing ancient sustainable construction techniques that have endured for thousands of years. The future preservation of the pyramids can be supported with a digital twin for managing historical sites. A digital twin would democratize data, include collaborative and participatory applications, engage and communicate how landscapes might change with climate change, and test strategies to enhance decision-making. Now let's take a look at GIS and Esri. Looking into the future, the GIS market is projected to grow from $12.9 billion in 2023 to approximately $35.5 billion by 2032. We recognize and think that much of the growth will come from digital twins, 3D GIS, and reality mapping. ArcGIS is a crucial component for geospatial digital twins. These integrated digital twins are comprehensive networks that interconnect content, behavior, and workflows, serving industries from infrastructure to smart cities. Leveraging ArcGIS, we create digital twins that unite diverse data models, supporting business processes, lowering risk, and promoting collaboration through realistic virtual representations. Digital twins in ArcGIS enable the integration of various data sources, including IoT sensors, real-time data feeds, and historical records, to provide a holistic view of assets and environments. This interconnected approach allows for continuous monitoring, predictive maintenance, and optimized operations. By interconnecting content, behavior, and workflows, we at Esri help organizations visualize complex systems, simulate scenarios, and make data-driven decisions. Reality mapping is the process of creating accurate digital representations of the physical world using images, LiDAR, or both. This process is a catalyst for developing digital twins, which are essential for modern urban planning, infrastructure management, and environmental monitoring. Automation enhances efficiency with technology, while democratization makes complex geospatial data intuitive and accessible for non-experts. The simplification helps overcome the 3D barrier, enabling users to interact with and understand three-dimensional data more easily. By leveraging these advancements, reality mapping transforms how we visualize, analyze, and manage our physical world. Building a digital twin involves several key ingredients: reality mapping, a system of record, ArcGIS Living Atlas open data, real-time data, and applications and solutions. These components work together to capture, integrate, and visualize data. This comprehensive approach enables advanced simulations, real-time monitoring, and collaborative planning, ensuring that all aspects of the digital twin are effectively managed and utilized for optimal results. Now let's take a look and see this in real life. Here's an example of a digital twin of the city of Stuttgart, Germany. Built with the power of ArcGIS, this digital twin has been enriched with other foundational content, combining reality mapping and GeoAI capabilities. The geospatial layers generated by reality mapping capabilities serve as a powerful means of visualization. They can be enriched with other 2D and 3D GIS data, such as building footprints, BIM models, and much more. These layers, embedded in the GIS, supported advanced simulations and decision-making. Here is an example where urban planning benefits from having a 3D mesh as a realistic context. Users can visualize exactly how the newly designed buildings may impact the neighborhood or local skyline. Large infrastructure projects can also benefit from reality mapping. This digital representation includes a BIM model, where users can explore the redesigned Stuttgart train station, from the way it gets integrated into the surrounding landscape, to accessing the interior of the future facilities and seeing a virtual representation of the experience as you travel down the stairs. Beyond visualization, this digital twin has predictive and analytical capabilities like flood modeling. This helps local governments and organizations identify how rainfall and water interact with the terrain. Leveraging GeoAI models and tools in ArcGIS help users to extract and identify assets within imagery. In this example, trees and vehicles have been identified. A digital twin is not limited to a static snapshot at one moment in time. It can also integrate real-time data, as you see in this example for live tracking of the city bus fleet. Or, in a similar application, public health can benefit from monitoring the city's air quality through real-time measurements. ArcGIS's capabilities allow for a deeper understanding and supports real-world decisions, as you just saw in this Stuttgart digital twin. Reality mapping covers a wide range of scales, from individual sites to entire cities, states, and countrywide applications. This versatility allows us to capture detailed geospatial data at various levels, providing valuable insights for different contexts. By integrating data from drones, aerial, and satellites, we can create detailed and accurate digital representations that inform decision-making at all these levels. For states and countrywide applications, reality mapping enables large-scale environmental monitoring, resource management, and transportation planning. At the site level, reality mapping can be used for precise infrastructure projects, construction monitoring, and localized environmental assessments like crack detection or tree clearances from power lines. This multi-scale approach ensures that reality mapping can meet the diverse needs of geospatial professionals, whether they are working on a small site or managing resources across an entire country. Understanding the resolution needed for different purposes is crucial when working with 3D data. Here we demonstrate the importance of scalability and resolution in the digital twin journey. On the left, you see a yellow blob. What could it be? In the middle, the blob becomes clearer, suggesting a utility box. On the right, it's evident that the object is a postbox. This progression highlights how different resolutions can reveal varying levels of detail, guiding us on what can be achieved. And our final look at different resolutions. Here we have two examples showcasing very high quality resolutions, down to 0.5 and 0.25 centimeters GSD. With Esri's powerful reality mapping, it's almost possible to count the blades of grass in the right-hand picture. This demonstrates the incredible detail achievable with advanced mapping technologies. With reality mapping products, we can create outputs from any imagery to create a DSM, True Ortho, Point Cloud, and 3D Mesh. These foundational products are essential for integration with the digital twin, providing a comprehensive and detailed view of the environment. The imagery serves as a system of record for further use and analysis, ensuring accuracy and reliability. And with ArcGIS, we are uniquely positioned as both a system of record and a system of engagement. We can leverage these foundational products in a new era of mapping and GIS to gain deeper insights and perform detailed analysis, such as identifying trees, cars, and defining building outlines and computing the solar radiation potential for green roofs and solar panels. With 3D GIS, users can visualize and analyze the world in ways that were previously impossible. For example, urban planners can model buildings and infrastructure in 3 dimensions, enabling them to assess the impact of new developments on the surrounding environment. Environmental scientists can study terrain and vegetation in greater detail, leading to more accurate predictions and better informed decisions. Reality mapping underpins all of this, providing the foundational data needed for 3D GIS applications. By integrating 3D data, organizations can enhance their spatial analysis, improve decision-making, and achieve better business outcomes. Here is an integration of a digital twin and open data. By leveraging open data from the city of Zurich, we can visualize the city's intricate details and infrastructure combined with the 3D mesh for contexts. Tourists and visitors can use this open data to discover Zurich in a more immersive and informed way. Here we have run a flood simulation in ArcGIS Pro to understand the potential impact of a flood in an urban area. This video simulates such an event in the city of Ljubljana, Slovenia, showcasing how advanced geospatial analysis can help us predict the water's paths, identify vulnerable areas, and plan effective emergency responses. By visualizing these scenarios, we can better prepare for and mitigate the effects of natural disasters. GIS interconnects and integrates seamlessly with the digital twin, creating relationships and streamlining workflows. Digital twins and 3D GIS are central to this integration, playing crucial roles in various stages. Accurate data collection and storage are achieved through modeling, system integration, and reality mapping. Real-time analysis can be done with dashboards for dynamic monitoring and visualization. AI and machine learning enable advanced simulations and forecasting, and sharing is enhanced with easy data access and collaboration tools. By integrating GIS with digital twins, organizations gain a comprehensive understanding of their assets and environments, leading to better decision-making and improved outcomes. How is all of this connected? We are an open system and use a connected data environment, integrating various sources through APIs for seamless exchange. This enhances our ability to analyze and utilize information, leveraging AI for insights. Portals for web maps, mobile workers, dashboards, and VR experiences connect data on demand, improving efficiency and decision-making. Let's take a look at some examples of a connected environment where data can be interrogated on demand in the office or in the field. When managing underground utility networks in the office or live in the field, the difference between 2D and 3D is significant. As infrastructure networks become increasingly dense, 2D representations fall short, risking accidents and financial loss. By combining 3D reality mapping with 3D underground utility vector data, we create valuable insights for many stakeholders. This integration minimizes risks at every stage of work cycles, including planning and design, analysis, simulation, inspection, and operation and maintenance. In this Boston Live demo, a 3D mesh is combined with real-time data feeds to create a dynamic 3D representation of Boston. With this combination of live data such as traffic updates, local crime reports, and emergency services information, city officials can visualize and manage the city's current state in real time. This approach enhances situational awareness and supports better decision-making and planning. This integration demonstrates how advanced mapping technologies can transform the operation and management of urban environments, enabling more efficient and effective city governance. Advanced tools like Airflow Analyst are used for analyzing and simulating urban environments. By leveraging 3D urban models and meteorological data, it is possible to simulate wind conditions and predict ventilation performance. These simulations help city planners assess wind-related phenomena, pollutant dispersion, and aiding in urban design and environmental management. Additionally, sunlight and shade simulations using existing 3D data and proposed building models allow planners to understand how new developments will impact light exposure in surrounding areas. This is essential for ensuring adequate sunlight in public spaces and minimizing unwanted shading. Digital twins combined with reality mapping, BIM, and urban XR enable data-driven decision-making by transforming comprehensive data into actionable insights. This integration allows for quick iteration and efficient issue resolution. By integrating with the GIS system of record, digital twins can create simulations while dashboards provide real-time visualization and analytics, enabling dynamic monitoring and response. The upcoming ArcGIS Urban XR will further enhance these capabilities, supporting advanced simulations, interactive dashboards, and game engine integrations. GIS content, including reality mapping, outputs, and 3D GIS data, can be streamed into game engines like Unreal Engine. This integration creates accurate and immersive visualizations, allowing for detailed and interactive exploration of urban environments. This integration supports applications such as urban planning, architectural visualization, virtual tourism, and emergency response simulations. Okay, now I'm going to take you through two very small demos just to show some of the capability within Reality for Pro. So I've got a normal Pro project here, and the first thing I want to do is go in and create a new reality mapping workspace. I give it a name, and I would choose workspace type reality mapping. I'm going to use drone data for the first one and just keep everything as is. For anything along the way, there is sometimes an info item or a link to go to some further documentation. And just another key tip about Pro is generally it works from left to right and top to bottom, so you can be taken through a journey in that way as also. Okay, I'm going to navigate to my folder of images. And okay, in this particular folder, I just have 6 images. This is not a normal project. A normal project would have hundreds to maybe thousands of images, but I just want to show you the functionality of the software. So the geolocation information is automatically read from the EXIF within the image. The spatial reference system is automatically determined based off the position of the data in the world, and some initial camera information is read, and we've just got to go through and confirm the particular details. If you have different information, this is where you would change it and fill it out. Otherwise, I'm just going to go with the default for now. Okay. Next, I'm going to load in my data based off the generic default settings of average elevation from image data. But if you had other options, if you had a DEM or you wanted to define a constant elevation, you could also. And in the advanced options, I'm going to leave everything on as default. So estimate statistics. Now what it's doing is creating a reality mapping workspace, and will build up all the relevant items I need to do the next steps. Okay, here you can see my 6 images, building the image collection, and there we go. As you can see, these are the images. Currently, they're not aligned. They've just been imported based off the initial GNSS information captured by the drone. So as you can see, there's minor misalignment now, which is totally fine. What we're going to do is we're going to adjust these images together, which will be a photogrammetric alignment. And as you can see, there's some other things we can look at here. We have the camera location. So these are just the XYZ. We have the flight path, and we have the image collection itself. So we could have a look at the boundary of the data. We can turn off the footprints, and we can turn off the images themselves. So everything is able to be turned off and on. Okay, so as we don't have any adjustment yet, we don't have any information in this first section. So as I said, we want to go left to right. So we're going to go to adjust. And within the adjust pane, we have multiple options. Really, really helpful is if you want more information on all of these different functions and features, click on this link here and it will take you to a public web page where you can understand what each thing means. As this is a drone camera, I want to do a full camera calibration, and I'm going to leave the rest of the settings on default for now. But as I said, if you go into this documentation, I'll explain a little bit further on what each of these different options do. Everything here is a balance between quality and speed. So items that will add quality might take a bit longer, and this is just a balance you need to strike for your particular data set. Okay, I've got these options selected. I'm going to hit run. Okay, here what it's going to do is actually two block adjustments. So for the drone scenario, it does an initial just to get everything a little bit closer, and then it does a final. As you can see, there's a first round of results. So the the GSD of this data set is 7 millimeters, which is really, really detailed. And we've got 6 images, and then it shares some of the information about the tie points and the solution points. Okay, so now the adjustment is done of this 6-image project. Took 1 minute. We have some results. We have the GSD of the project. We have the mean reprojection error, and we have some other information. So we are basically good to go. And as you can see, compared to before, there's slightly better improvement of these images, but don't worry about this because we're going to do some reality mapping products. As you can see, we don't have any ground control points, but if you had some ground control points, you could import them, through here, import ground control points. So this is from a TXT file, CSV, where you have the point ID, the easting, the northing, the height, and you need to define the spatial reference to be able to import them and visualize them. And then you can click them in the Manage GCPs tab. Okay, so what I'm going to do now is create some products. So because it's just about showing the software, I'm just going to do a very small version and just do the DSM and True Ortho as per that. If this was an oblique project with multiple cameras, I would choose 3D point cloud and 3D mesh. And if I wanted a digital terrain model, I could also choose that in here. So as per similar to the adjustment settings, we have different settings available for the reconstruction. We have ultra and high, and similarly as per the adjust settings, we have this link down here where you can find out more information what each of these different steps and features and qualities mean. So please go there for further information. I'm just going to choose high, and I'm going to leave everything else as default. But I'll just quickly go over product boundaries and area of interest. Correction features is if we have a shapefile that we want to correct certain levels down to, or up to. So if you have like building footprints and you know the height of the building and you want to force the dense matching and the photogrammetric steps to be at that level. Water body features, if we have water body, in this case we don't. And we can also define the processing folder of where the work is done and where the results get sent. Okay. So as I said, please head on down to this link if you want more information. Okay, I'm just going to hit OK with defining these settings. And then the next thing it wants me to do is define what type of outputs I want. So I can choose tiled or mosaic. Let's choose tiled for one and mosaic for the second, just for argument's sake. Because in the mosaic setting, I just want to show you can define a couple of different formats. So straight to a CRF, cloud raster format, or TIFF. And you can also define different compressions, different resampling, that kind of thing. So totally up to your control and what you want to choose. Okay, I'm just going to hit finish. And let's wait for some reality mapping products. This should go reasonably quickly as it's only 6 images. And let's see. Okay, so the project's finished on my computer. As I said, this is just a 6-image demo, so don't worry too much about the runtimes here. So we can close this and let's have a look at the results. So first of all, we have a shapefile that defines the running status of the project. So this changes color while it's processing. And now that it's fully processed, it's done. So it's this darker green, so I can turn that off. And what I have also is I can turn off the image collection underneath. And now what we end up is a true ortho. I will also turn off the camera and the flight path. Now we have a true ortho from 6 images and a DSM. So, and here is the DSM underneath. So as I said, with 6 images, not the best quality, but I just wanted to show you the easy workflow it is to get to this point. Okay. Okay, let's do one more quick demo with some satellite imagery, and after that I'll just showcase the results of these 2 processes, the full runs in ArcGIS Online, where I've published them already. Okay, so let's start a new workspace as we did before, and this time we are going to process some satellite imagery from provided by Black Sky over the pyramids of Giza, which is super cool. Okay, so I'm going to choose the Black Sky sensor type. I'm going to navigate to this data set. Okay. And it automatically, so I've just navigated to the folder where all of my images are, and it's automatically chosen again the workspace reference system, which is good, and multispectral, and I just want to change this band order quickly. So red, green, blue, and all of that is good. Multispectral, fine. Finish. Now I'm going to import these images and do exactly the same basically as before, some slight differences with the satellite settings, but more or less the workflow is the same. Okay, so we've imported in all 15 images. If I zoom in, they will appear and we can just inspect what they look like. You don't need to do this, but I just want to confirm that they exist, which is great. They're not aligned yet, not a problem. Similar before, all the same setup. We want to go left to right, top to bottom. So let's go straight to the adjust. And within the satellite options, we have slightly different choices, and we want to use RPC. And again, we can go into the link here to find out more settings. I'm just going to leave everything as default. Also, that's because the RPC values on this particular sensor and a few of the other sensors are already quite good, so you don't have to play with many settings. So let's hit run. Okay, great. That took 44 seconds, 10 seconds, so about a minute and some change, which is really great. Again, we have some more results. Don't have any ground control in this case again, but often you don't need the ground control for the satellite, and potentially you actually cannot see the ground control points. There are ways in which you can connect the ground control points to the base map, but that's something we can talk about in person. Okay, so we've got our alignment. I'm happy with all of that. What we're going to do now is the same as before. We're going to choose our products. So in this case, we have just 2D products, but we have actually the DSM mesh, so it's like a 3D mesh. So let's do digital train, model, true ortho, DSM, and DSM mesh. And then let's leave quality ultra, and we're just going to hit OK, and then we're going to hit run. So again, we need to choose our output types. So I'm just going to choose tiled. As I said before, I can choose mosaic. And for the DTM, you can change some settings. I'm going to just leave it as default, but this is when you can use your expertise to define different settings. And for the true ortho, again, tiled, I'm going to choose, and the output for the mesh, I can choose 3D tiles, SLPK, or OBJ. So I'm going to hit finish there. Let's skip out of here, and I'm going to now show you the results of the mesh in both the first drone demo I did and then the satellite demo, and then we're finished. Okay, as I said, let's just take a little bit of a spin around the final results of the complete data sets that I showcased. So this particular data set here has a full 5-camera oblique system from a drone. The demo that we ran just had an idea, so we've got a lot more detail here on the facades. We can zoom in and we can get some really, really nice detail once it loads on my internet. Perfect, there we go. So this is what you are capable of on your own with this software. Now let's jump over to the satellite dataset. Okay, and here we have the Giza pyramids collected from the Black Sky Imagery. Again, this with the demo I gave, we used all the images in the adjustment, but I didn't wait for the final reconstruction to be completed. But this is what the 3D mesh would look like. So we have a true ortho and DSM additionally with this, but just wanted to show the beauty of the Giza pyramids in Cairo. Super nice, really, really nice. So that's how easy and simple it is to process some drone projects and some satellite projects in Reality for Pro. We also have another tool available, or another solution called ArcGIS Reality Studio, and this is specifically for aerial solutions, for aerial mapping. And if you have any questions about that, please reach out to your Esri distributor or myself or one of your Esri friends. Thank you very much. This final video showcases the comprehensive capabilities of a Zurich digital twin with data courtesy of Stadt Zurich and Wingtra. By combining reality mapping and 3D GIS, various aspects of the city's digital transformation are highlighted. The digital twin includes assets across the city: a detailed 3D base map, reality mesh, interior spaces, BIM of the train station, laser scans, live sensor integration, future journey simulations, and elevator sections. By integrating these diverse data sources, a Zurich digital twin provides a holistic view of the city's infrastructure and operations. This powerful tool supports urban planning, enhances operational efficiency, and improves public safety. The ability to simulate future scenarios and monitor real-time data ensures that Zurich can proactively address challenges and optimize city management. Thank you for listening, and if you want to reach out for more information, please connect with GISTech or reach out to me on LinkedIn via this QR code or my email address. Thank you.